Hello everyone, welcome to another episode from Chedexcel. Today we are going to talk about bond enthalpy calculation. Now, bond enthalpy calculation is the third and the final part of enthalpy calculation that normally come for Unit 2 paper. So we'll see how we can use bond enthalpy calculation or the bond enthalpy data to find the enthalpy change. Now, in the previous two lessons, we discussed how we can calculate the enthalpy change using the formation enthalpy data and how we can calculate the enthalpy change using the combustion enthalpy data. So today we are going to talk about how we can find the enthalpy change using bond enthalpy. Right. First we look at the simple use for standard enthalpy change of bond dissociation or standard enthalpy of bond enthalpy. Right. This is commonly given delta T H standard, or we can take it as delta H standard D. This is commonly the enthalpy change for the bond dissociation. The definition for the bond dissociation is given as the enthalpy change when one mole of gaseous bond is broken to produce the gaseous atoms. So it is important to know it is enthalpy change when one mole of gaseous bond. For example, delta T extended Cl2. That means chlorine gas is broken to produce two Cl gas atoms. The Cl-Cl bond is the one we break here, right? So this is the enthalpy change when one mole of chlorine gas is broken. Then what about the enthalpy change of bond dissociation comes to HCl. So HCl, H gas and Cl gas, right? So this is how we write the standard enthalpy change for the bond dissociation. It always represents the one mole of gaseous atom. Now, there are cases that the molecules contains more than one mole. For example, let's take about CH4. If we apply the bond enthalpy for CH4, it is carbon gas and 4 hydrogen gas. And you can see in CH4, you have 4 CH bonds. 1, 2, 3, 4. And actually the bond enthalpy value for each C and H bond is different, it's not the same. So if the bond enthalpy values are different, the values are going to be different as well. So commonly we use, if there are more than one bonds in a gaseous molecule, we use something called mean bond enthalpy value or average bond enthalpy value. Because not only for CH4, any molecules, the bonds get the enthalpy value for the bond dissociation will be different from compound to compound. The CH bond of methane is different than the CH bond of ethane. CH bond of alkenes are different than the CH bonds of alkanes. So theoretically we have different values, so we can't use them one enthalpy value for one instant, or the different instances we can't use different enthalpy values. So obviously we have to have an average value to use in calculation. So we use the idea of mean bond enthalpy value. So in this case, this is not delta D CH, this is delta into 4 times. This whole process is enthalpy change of CH bond dissociation into 4 times. It's not just one. Let's say another one like this. Okay, I'll put Cl here, H, H and H. So if we break this into gaseous atoms, we have carbon gas, hydrogen gas and Cl gas. 1, 2 carbon is there, 3 hydrogen is there, 1 chlorine. So if you apply the bond enthalpy or bond dissociation enthalpy for this one, right, it's not just one value. So what is the bond enthalpy for this particular one? The bond enthalpy for this one would be delta D H carbon carbon double bond plus 1, 2, 3. 3 delta D H CH plus 1 CCl D CCl. So the summation of all these enthalpy values are the one which actually represent the enthalpy change for this particular reaction. So the summarize is bond enthalpy is the breaking of a gaseous bond, and when you have more than one bond type, you have to add everything get the enthalpy change. Now this can only be applicable for gases. So when we have a solid liquid, we can't actually use it. But in chemical calculation, we use them. So always the value we get would be different. So in a bond enthalpy calculation, the enthalpy change at the end would be different due to two reasons. The first reason is the physical state is not the gaseous state at the time when we do the calculation. That's one reason. The second reason is we use average or the mean bond enthalpy value for the calculation. So the enthalpy changes depends on chemical environment. So those two reasons are the reasons why the calculated enthalpy value would be different from the actual enthalpy value. So we'll do two questions and see how we can apply this. So again, as I told for the previous two method, we can use the equation for this, or we can draw a Hess cycle for this. So we'll see what are those two methods. So the two methods we can use to find the enthalpy change of a chemical reaction using the bond enthalpy changes. First one is using the Hess cycle, second one is using the formula. So we'll see how we can construct the Hess cycle using the mean bond enthalpy. Right. There are a few steps. The step number one, you will write the balanced chemical reaction on top. Step number two, write the gaseous atoms at the bottom and balance it. Step number three, put the arrows from reaction to the atoms or top to bottom. For example, CH3 CH double bond CH2 plus HBr. You have CH3 CHBr CH3. So we have asked to find the enthalpy change of this reaction, right? So this is the reaction we are going to do, and we will be given the bond enthalpy values. So I put those data. Some data you might not need, but I put the data of this value. So how do you construct this one? Now, first step is write the enthalpy change of to find the enthalpy change of this reaction. This is the enthalpy, means the data you are given. Then we write the balanced reaction. Then write the gaseous atoms at the bottom. So what you get? Carbon gas, hydrogen gas, Br gas. Now carbon is not a gas, but to do this we have to write it in the gaseous state. And you have to balance it. 1, 2, 3. 3 carbon atoms are there. Hydrogen 3, 2, 4, 6, 7. 7 hydrogen atoms are there, and 1 Br. So that's balanced. Then arrows from top to bottom. So this is how the arrows comes. Then we can apply the Hess law. So what is the Hess law? When you apply Hess law comes like this. These two is equal to this one. So and say delta RH plus. Now how many different types of bonds are there? So that's why I told you it's better if you can draw the displacement formula. So if I write the bond displacement formula, this is something like this. So how many what are the other bonds? We have to make 1, 2 CC bonds. I am not writing the delta H part, it's fine. 2 CC bonds, right? Yes, so that is done. 1, 2, 3, 4, 5, 6, 7. 7 CH bonds, that's also fine. 1 CBr. So those are the bonds that we have to break in order to form this gaseous atoms. So delta RH plus 3 is 3, 1, 2, 3, and then CBr. That is equal to this side. So if I draw this again, I can draw it here. H, and HBr. This one is like this. So 1, 2, 3, 4, 5, 6. 6 CH bonds are there, plus 1 CC bond is there, plus 1 C double bond is there, plus 1, right, that's it. 1, 2, 3, 4, 5, 6 CH, 1 CC double bond, and HBr. So those are the bonds you have to break from the reactant side. Now you can substitute the values, right? So these are the values, and if you substitute these values, we'll see how we can do this. So delta RH plus 2 CC value. So CC is 3, 4. 347, 2 into, you will be given the enthalpy changes, plus 7 into CH413 plus CBr, which is equal to 290 equals 6 into CH413 CC347 CC double bond, which is equal to 612, and HBr value is 366. So you can calculate and get delta RH. That is how we find the enthalpy using the bond enthalpy data, right? This is how we do the enthalpy using the bond enthalpy data. So it's not that hard. So if we apply the calculation, we can get the value, right? So I'm not going to do it right now. So we can get the enthalpy. So this is a very first way. Now there are another ways you can do. You can cancel out 6CH with 7CH. So before you substitute the values, that's one easy way. But this gives you the easy way of, this is how you construct the Hess cycle using the bond enthalpy data. Let's see what you can get the other way. Other way around is, that is a formula. So the formula is, now if you do, this is what delta RH plus, this is summation enthalpy of bond dissociation of what? This is products, right? Products equal, this side is reactants, summation enthalpy change of bond dissociation reactants. So we can use the formula for the rest, that is sigma, that is summation bond dissociation of reactants minus summation bond dissociation of products. So reactants minus products, that is the common thing we can use when you do the bond enthalpy calculation. Some questions are, they are very easy. So this is the way you can do it. It's very easy one, right? Actually you have this one in IGCSE, O level as well, right? This is where we do it in AL. So bond enthalpy calculations, not that hard. So we'll do quickly one more thing, and this is the reactants minus products. We can use that as well. So we'll quickly do another one. Another example. Right? So we can construct many Hess cycles if you want. For example, something like this. CH3 reacts with oxygen, you get CO2 and H2O. Right. Sometimes you might ask you to balance this by yourself as well. So how do you balance the organic reactions? Very easy. First you balance according to the alphabetical order. Carbon to hydrogen to oxygen. 2 carbon, put 2 here. Then hydrogen, 3, 3, 6. Then put 3 here. Then oxygen, 2 and 2, 4. 4 plus 3, 7. Then you have 7 over 2 O2. Right? So that is the chemical reaction. So if they ask us to find the enthalpy change of this one. Now we can find enthalpy change of this reaction using the formation enthalpy data. CO2, H2O, this one. We can find this enthalpy change using the combustion enthalpy data, but that's what they have given over here. We can find the enthalpy change of this one using the bond enthalpy data. So if you write the bond enthalpy, what you write is, you write the gaseous atoms at the bottom. So carbon gas, hydrogen gas, and oxygen gas. 3, 3, 6, 7 over 2, that means 7 oxygen and 2 carbon. So we write the reaction on top, gaseous atom on the bottom. Arrows down, top to bottom. So this is the way we construct the Hess cycle for this. Then again, you can either draw this one, or you can just write delta RH enthalpy change is equal summation bond enthalpy of reactants minus summation bond enthalpy of products. reactants minus products give the enthalpy change of this reaction. That is how this is what we derived earlier. If you apply this delta H, that is equals reactants CH3 that is 1 cc. See, this is like this. We have 1 cc bond plus 6 CH bonds plus 7 over 2 oxygen to oxygen double bond. So these are the enthalpy change of reactants minus products. Products means this one. 2 CO2, 2 molecules CO2, you have 2 double bonds, 2 into CO plus H2O, 3 into 2 OH. Then we can substitute the values and we can get the results. So CC double bond, CC single bond is 347. 6 into CH is 413 plus 7 over 2. Oxygen double bond is 498 minus 2 into 4 into CO. Carbon oxygen double bond is 743 plus 6 into OH 464. So this is just a simple addition and you can get the value. So if you apply the value, it will be 347 plus 6 into 413 plus 7 over 2, that is 3.5 into 498. So 4568 here, 4568 minus that side value 4 into 743 plus 6 into 464, 5756. Minus 1188 kilojoule per mole. So this is how we do the enthalpy calculation based on bond enthalpy data. So we learned how to construct Hess cycle, we learned how we can use the reactants, the formula, and that's how we use the bond enthalpy calculation. Right. So we learned how to find the formation enthalpy, combustion enthalpy, and bond dissociation enthalpy. And I put the links for those two as well. You can look at them if you want to see how we can find the enthalpy change using the formation enthalpy and the bond and the combustion enthalpy data as well. So that's it. That's how we find the enthalpy change using the combustion enthalpy, the bond dissociation enthalpy data. So if this is helpful, give a thumbs up and consider subscribing. Thanks for watching.